All right, here we go. This is problem number 3 from chapter 9 of the Halliday and Resnick textbook. We're trying to find the center of mass of this shape here. So I guess before we do get too far on it, let's point out that half of it's iron, and we're given the density of the iron, right? And the other half of it's aluminum, and we're given the density of the aluminum. And then the other thing I notice is that it's symmetric along two different axes, right? Really, the only uh, you know major calculation is the fact that along this axis, along the y-axis, there's one end that's going to be heavy because of the iron, and the other end that's going to be a little bit lighter because of the aluminum, right? But along the other two axes, our center of mass is just going to be at the center. Okay, so what that means for us then is our x center of mass is just going to be half of, it looks like d3, right? Because the x-axis runs this way, right? So it's going to be just half of d3. So our x center of mass is going to be half of 13, specifically 6.5 centimeters. All right, and similarly, our z center of mass is going to be half of, it looks like d2, right? Because the z-axis runs this way. So d2 is 2.8. So our z center of mass is going to be 1.4 centimeters. So the only thing that remains then is to find our y center of mass. All right, so here's what we're going to do. We're going to the obstacle here is the fact that we've got it's non-uniform density, right? It's not symmetric. Um, so what we're going to do is we're going to break it up into two chunks. Okay, what I'm going to do is I'm going to condense this iron block down to 1 point. Okay, so that the iron rather, can be treated as having a location of, well, if you look just at the iron block, it's symmetric. So along the y-axis, our center of mass should be, well, that's the worst straight line ever, just right at the center, right? So D1 is 11. So that means that the center of mass of just the iron should be half of 11, right? So 5.5 centimeters. Okay? And then similarly, for the aluminum, its center of mass is going to be right here, which is going to be at a position of 11 plus another half of 11, so 5.5. So 11 plus 5.5. So the y position of the aluminum is 11 plus 5.5, so 16.5 centimeters. Okay? So now what we need to do is find the overall center of mass, right? So here's the trick with this. Let me get a skinnier pen here. All right, so our y center of mass is going to be, well, that should equal the mass of iron times the y position of the iron plus the mass of aluminum times the y position of the aluminum over the mass of iron plus the mass of aluminum. Okay, but, so here's the trick. We're not given the masses specifically, but what we are given is the densities. All right, so I guess there's two options. Option one is this. So, for example, let's look at the iron, right? So if you look at the iron for a minute, the iron has a density of 7.85 grams per cubic centimeter. So if we figure out how many cubic centimeters there are of iron, then multiply by 7.85, that would give you the mass of the iron. But I'm not going to do that. Here's what I'm going to do. Check it out. I know that the mass of iron should be equal to the density of iron times the volume of iron, right? And the mass of aluminum should be the density of aluminum times the volume of aluminum. But notice that the volume of iron and the volume of aluminum are equal, right? Because, they're both the same size. They both the block of iron and the block of aluminum have the same length, width, and height. Okay? So, I'm going to replace V here with, I'm going to replace VI with just V, right? As in the volume of half of, this whole shape, right? Same here. So watch what happens. Down here, I'm going to replace mass of iron with the volume times the density. So this becomes the mass of iron is the density of iron times the volume times the y position of the iron, plus the mass of aluminum is the density of the aluminum times the volume times the y position of the aluminum, all over, let's see, the mass of iron is the density of iron times the volume plus the density of aluminum times the volume. Hopefully you figured out by now this Greek letter rho is usually what people use for density. Okay, so anyway, if we look at this expression here, you hopefully notice that, oh, if I divide the top and the bottom by v, all of these v's cancel out, right? So I'm left with this. It's density of iron times the y position of the iron plus density of aluminum times y position of the aluminum over density of iron plus density of aluminum. Okay? All right, so now we can just plug in our numbers, right? Let's see, the density of the iron is 7.85. I'm going to skip the units because they're going to cancel anyway. Times the Y position of the iron, that's 5.5 centimeters. Plus, same thing for the aluminum. Let's see, its density is 2.7. Times its position is 16.5 centimeters. All divided by my total density, which is a weird thing, but you can solve that. And you end up, if you solve this, if you simplify this expression, you get 8.32 centimeters. So there's our Y center of mass, 8.32 centimeters. So then obviously you could write this as an ordered pair. Okay, so there you go. That is that.